Thank you, to the organizers for inviting me. All right, so this is based on joint work with full titles. The most of what I'm going to say is we have a paper archive, but there's sort of the theorem we proved. The paper was already like a long paper, and so there is a statement, fluid theoretic statement that is an assumption that it is the theorem, and I will explain how to. So one way to remove that here. So I'm gonna compared to what we had this morning, I'm going to talk about a very simple form of global within theory, which is just a Fano manifold or monotone symplectic manifold. If you're pleased with symplectic geometry, I'm going to just include one variable. And I'll look at this kind of quantum connection here, where the quantum product is, I'm just basically the superscript of the degree is just the degree of the curved class that's contributing to the product. So Q is the degree 1 classes squared, the degree 2 classes, and so forth. What I'm interested in actually are the singularities of this connection. So just by inspecting it, there's an obvious singularity at 0. There's also a more interesting singularity at infinity, which is primarily what I'll talk about. Well, basically everything I'll talk about. So I just want to review the terminology a little bit. So you have a meromorphic connection, and sort of the simplest singularity is where you just have kind of a pole. Well, up to gauge transformation, you have a pole of order 1. And so in that case, I just want to remind people that you can do a further gauge transformation and actually make this sort of transform so that AQ is like this Q inverse times a constant matrix, and then and the monodromy is then the exponential times minus 2 pi I times that constant matrix. So the monodromy will be something I'll talk about quite a bit. The next sort of case that one sees a lot in the literature is this what's called unramified exponential type, which means that one can put the connection, break it into a direct sum of these pieces where you have sort of a regular part, and then the pole, this lambda k is just some complex number. So, it's basically a regular. So this regular piece here is basically well defined, or at least it's monodromy well defined. So there's sort of regularized monodromy that one can attach to such a connection around, associated to each sort of each of these complex numbers. So here's the main, so again, let's look at the quantum connection. So you take a grading operator, which we saw earlier, and the grading operator that, in this case, I'm looking at it, so we take, the homology class. So if we're just looking at the degree piece, if D is even, it's literally just a degree, but otherwise, we're going to take alpha and multiply it by 2 times the floor function of D over 2. And if you do that, then you can write down a gauge transformation that sort of clarifies the structure of the connection a little bit. So again, Q equals 0 is not very interesting, but at Q equals 0, what you have now is basically something with a degree 2 pole times a constant matrix, and so basically have a degree a second order pole and first order pole term. So these kind of connections are very studied a lot in the literature by Sabah and other people.
So the first equation, we think where is the quantum product appearing when you say the connection is originally like the conjugate one?
Oh, so
The first equation says that it's a definition, right?
Oh, first, so the quantum product, the definition of the quantum connection is here, okay?
No.
And,
Thank you. That's fine.
and then so you have the derivative of so it's written that, yeah, this is the capital Q is 1 over Q. So I'm looking at the neighborhood of infinity. So the main result that we proved is that if you have a smooth Fano manifold, or well, you can say something in more symplectic language that I'll just elide here. But you know, any symplectic geometer can probably guess what it says. But in any case, so you have a smooth. Oh, how are we doing? Okay, great. So you have a smooth Fano manifold which carries a smooth anti-canonical divisor, and then the quantum connection has a singularity on ramified exponential type at infinity, and then furthermore the regularized monodromies at infinity, so meaning the monodromies of those regularized connections for each of those pieces of the decomposition are quasi-impotent, so meaning they have eigenvalues of unity. And then there's an also so those are sort of the main pieces of the theorem. There's also a kind of a bound that we obtained on the sides of the Jordan blocks of these monodromies, of these regularized monodromies that I'll mention maybe the next time I speak, whenever that is. I'm not sure, but what the schedule is going to look like. Okay, so I want to sort of go through sort of a mirror symmetry motivation for why you might. Oh, I should say that obviously this statement here we sort of found it. This statement is we found it in the paper of Galkin, Golechev, Miritani on the gamma projector. Sort of maybe explain how it's related to that. The other thing that this theorem allows you to do is to define quantum spectra. So that's probably the more immediate application. So that's another thing that I'll talk about in my second talk. Okay, so the mirror symmetry motivation is sort of a classical mirror symmetry picture, like again, maybe Sabah and others. So you want to, the mirror to having a smooth anti-canonical divisor, that there's some smooth, that there's some proper Landau-Ginsburg model. So meaning the fibers are going to be some kind of compact. Well, the total space Y will be a non-compact Calabi-Yau, and its fibers will be some kind of family of compact Calabi-Yaus with some singularities, and then so using the function, you can sort of twist the de Rham differential, so the de Rham complex of Y becomes a module over the de Rham complex of the base, and there's sort of a standard twisting that you can do. So the de Rham complex acquires a circle action, and you kind of form the invariance of that, and there's also a connection. So it's like a functor from module of the de Rham complex to D modules. And if you apply that functor, and you in this case you obtain the Gauss-Bonnet system, and it's sort of a classical fact that the hypercohomologies are, to take this connection, the hypercohomologies are holonomic D modules over the base, and furthermore, so if you restrict it to C star, so it's not, it won't be a vector bundle, it'll have sort of the fiber over, you'll have sort of large, set Q equals 0, you'll have a large sort of fiber, but if you take out 0, and restrict to C star, then you get a vector bundle of connection, and you have a regular singularity at Q equals 0, and one of these singularities of a unramified exponential type at Q equals infinity. I'll explain why that more about how that works in algebraic geometry a little bit later.
This would be a section. The tool state of play smooth.
Yeah.
Any section on the zero fiber?
No. Okay, so we're basically the idea here is to try to take the mirror symmetry picture and take out mirror symmetrize it, and sort of just translate everything into non-commutative geometry terms, and make the proof in non-commutative geometry. So it's sort of a well-known thing in Miami since I was a student that the mirror to if you just start with the Durand complex of Y itself, sort of ignoring, the different, putting different, just considering differential forms on Y without the Durand differential or this twisting is mirrored to symplectic homology. So let's start there. So the basic idea of symplectic homology is kind of a Flair theory of the complement. So what we do is we more precisely take out sort of a standard tubular neighborhood of E, sort of thinking of it as a symplectic Monora bundle, a symplectic vector bundle, and there's sort of a standard structure, and by Weinstein's theorem you can write down an embedding of a neighborhood of 0 and excise that, and so the boundary becomes sort of a circle bundle, and moreover, so again, since we remove the complement is now an exact symplectic manifold, and you can also arrange that the sort of primitive of for the symplectic form that has a certain standard on this neighborhood. So in particular, you could the boundary becomes kind of a nice contact circle one. And so you have the sort of, whenever you have one of these sort of so-called Newville domains, you get sort of a nice Newville coordinate, and you sort of you can write down these standard functions that look like, so the boundaries will be at R equals 1 here. And then the sort of linear of slope lambda, and then, well, you have to take lambda sort of to be non-resonant. But you sort of, then you smooth this out. And what happens when you smooth this out is you get kind of, if you calculate these things out, you get a bunch of periodic orbits for the Hamiltonian. And then, for symplectic homology, you sort of you want to take the limit as lambda goes to infinity. So you get more and more periodic orbits here. And in fact, in this case, it's really straightforward to analyze what's going on. So the orbits sort of come in these, two types of families. Really, you have kind of constant orbits in the interior. Well, sort of here. I mean, I'm sort of giving just an approximation, but basically you want to think that you have sort of the place where the Hamiltonian is 0, those are kind of constant orbits, and it's a little bit heuristic what I'm saying, but basically true. And then you have sort of families that are copies of the circle bundle that wind around the divisor more and more time. So there's a winding multiplicity around the divisor, and then So because we're in the exact setting, there's sort of a natural, you don't have to, the word just talk, the functional sort of, you have to lift it to a covering space of the loop space, but here there's sort of a natural functional where you just integrate this primitive I was mentioning. So AH will be sort of just the integral minus the integral, I guess is my typical convention of this primitive plus, so this is on a Hamiltonian, on a loop, so, and then integral of T x naught to UT. And what you do is if you sort of arrange things really carefully, basically this functional is almost basically just a winding. If you choose Hamiltonians that are very, very close to this picture, the standard thetas and so forth, and you make the size of the two-drill neighborhood as well quite small, and then basically the functional basically is measuring the winding number. Also, you want to kind of assume that, and what this gives you, so it is basically is a nice way to sort of think of this symplectic homology, it's the kind of deformation of the topological picture where you have sort of the constant loops. This involves a little bit of more thought there, but it's not difficult. Where if you filter by this winding, then you got a copy of the homology of X or X bar, and then a bunch of copies of the homology of the circle bubble. And you get a spectral sequence from that to this convergence of this symplectic homology. And most of what I've said, by the way, works for a general smooth divisor. You could do it in normal crossing divisors if you like. There's a version of that that's more painful but possible. But the thing that's good about the anti-canonical case, basically, that this grading are actually the spectral sequence. These are the actual grades. Homological grading are the gradients. So you have basically the symplectic homology in this case is concentrated, in particular, in bounded non-negative degrees, which is entered into our proof actually. So that's sort of mirrored to the fact that the Durand complex is concentrated in bounded degrees, which is not going to be kind of a general non-commutative intelligence in arbitrary category. You're talking homology in all kinds of degrees. So I'm going to call this thing here H star log. It's just something I made up years ago, and I don't know. I'll stick with it. So I just want to remind again, say something basic as well. Just there's a standard way. If you have a compact symplectic manifold, and you're looking at Hamiltonian polarity theory of a compact symplectic manifold, there's a standard way to relate cohomology, classical quantum cohomology, to that Hamiltonian polarity theory, which is due to, well, I think maybe Siegel is involved, and Uniquin, Solomon, and Schwartz. And what you do is you sort of look at a continuation map on a basically some kind of thimble. So you put a Floer equation, which is at least at infinity, you want it to be holomorphic. If not, I mean, usually make it holomorphic even in the neighborhood of infinity. And you ask the mark point. So there's some equation on this thing which is holomorphic in the neighborhood of 0. And here near 0, you would sort of put a cycle here. And you would ask that the mark point pass to the cycle, and at the other end you have kind of somewhere near this puncture, you have Floer's equation, and you ask that at this end the asymptotic to a Hamiltonian orbit, and that gives you kind of a map from quantum cohomology to Hamiltonian Floer cohomology. So what I want to do is sort of do a version of that that's in this kind of divisor complement situation. So we look at kind of a log, well, again, log version of it or relative version of it. So if you have an orbit in the complement, so in X, then what a log PSS solution is basically, it's a PSS solution where this point, instead of passing through some cycle in M, it passes through the divisor with some. So the only additional condition is that it pass through the rest of the curve should lie in X, the complement, and this point here should pass through a divisor with some tangents. And so you can talk in this anti-canonical setting, you can calculate the dimension, expected dimension of these kind of moduli spaces, just the degree of the output orbit, and also there's a notion of energy for these solutions, and it's basically just W plus the action of the output. And we want to try to use this to kind of define classes in symplectic homology. So, so for any W, you sort of make a basis of. We also include you include W equals 0 as the kind of the unit in X, so there's no intersection multiplicity, and the rest of them are sort of just counting these PSS classes, which if so we're just going to count the ones where the degree is 0 and make a chain map to, or you get classes in this degree 0 symplectic homology. More generally, by the way, this is sort of relevant to what we want to say here, is you can also sort of take a cycle in the divisor and make a map from, say, H star B for W bigger than or equal to 1 to the appropriate degree symplectic homology. There's some small differences with the classical picture. So, one thing that can obviously happen is when you try to make a map is that there are, the Hamiltonian, if you sort of use this sort of limiting version or this model version, the Hamiltonian actually is constant along B. And so there's a bunch of orbits actually in the divisor. But what you can prove is that there's no, as long as your slope of your Hamiltonian is sufficiently large, then compared to your intersection multiplicity, then there's that breaking is not possible. And it makes sense because you can't really, you need the slope to be large if you're going to define, if the slope is small, you don't expect to have kind of canonical classes of flirt homology for every winding number. So, and then there's also some sort of sphere bubbling that you need to take care of, but let me not worry too much about that. But that's only sort of, there's something a little bit smarter you can do, or you can try to do anyways. And so I just want to, which is that actually, because there's kind of a canonical, you're thinking of this PSS solution as being a copy, as being like C, and there's a coordinate on there. So there's actually evaluation from, in that coordinate, basically, your map is a holomorphic map. You're 0, and you can take a sort of, you can take a local coordinate such that your divisor is, so that B is locally cut out by 0 cross Cn minus 1 inside of here. And you're imagining that you have a holomorphic, so there's a projection, I'll call it pi C, down to C. And locally, if you stand out, so you start imagining, you just take the piece where the map is holomorphic, it maps into something, you take a piece that maps into this local coordinate chart, then pi C. What? Larger.
Yes.
Okay. Pi C So this is just a map to the first factor, composed with this solution, U, or E, I guess, I don't know, is, you know, the locally it'll have an expansion, which is going to be the contact order plus some higher order Taylor, you know, so called Taylor expansion, where the first term is Z to the W, to the contact of order W, and the remaining terms are O W plus one. And you know, if you think about what this means intrinsically, like you change coordinates, you know, just sort of the local coordinate, and just think about what it means, you know, in intrinsic terms, this here is naturally an element of the normal. And so you're going to map, you know, and then you can take it's a non-zero element. You can think of it as a line of the circle bundle, it's projectivization, let's say, and you can try to put constraints in the circle bundle. Now that creates some problems for you, because if you think about bubbling in that case, so if you have we're imagining you have some constraint here, so it creates some additional issues, because if you think about, you know, you imagine some sort of degeneration, there's sort of, you lose a degree, like a gluing parameter. So you imagine like you have a contact order one and it bubbles into something where you have a contact order one here, then you can't really, with this thing, it's shed its constraints, you can't really rotate it. So if you use these kind of moduli spaces, bubbling becomes kind of codimension one. So we can't really, so far it's not really known how to actually, you know, use this to define kind of a full sort of PSS map that you might want to define, but what you can define is if you sort of just concentrate only on those orbits which have exactly the same winding number as your tangency, then you know the energy by the calculation I showed is like very, very low. And so then basically, you know, there's no bubble possible. And in that case, what you get is kind of a nice map from this law of cohomology to this first page of the spectral sequence. So it's, which is useful for various things. At least obtaining partial information about symplectic cohomology. Okay, so now I'll sort of get more to the point. So it's sort of a, you know, due to Kontsevich and so on, there's, you know, an infinity structure that naturally lives on symplectic cohomology, or, you know, any Hamiltonian Floer theory, really, which is sort of by thinking, doing sort of parameterized Floer theory over these configuration spaces of points, which are, you know, up to, so the configuration space of points of D points on C, up to translation and rescaling by positive rescalings. And you know, this actually admits sort of a manifold of corner structure, and if you sort of do Floer theory over this in an appropriate way, you get an L infinity structure on symplectic cohomology. So what I want to do is I want to take this, you know, this first W equals 1 class here, this sometimes, you know, called the Borman Sheridan element, but I don't know. Basically, just because of the degree calculation I showed, in this case, well, you have to do what I said at the chain level, so it's sort of, but it's, you know, symplectic cochain appropriately or in non-negative degrees. So you really, if you just take this class and multiply by Q. So my Q parameter here has, I'm thinking of it as having degree 2, that gives me a Markov solution. I don't, you know, in general, for general divisor, I would need more terms that I would need to add, but here this leading order term is all that I need. Just like a super, you know, this theta, you want to think of it as being mirrored to the super angle. and the W function I had before. And then I just use that to twist the symplectic homology. And this is my, well, this is what is going to be, is sort of mirror to, if I go all the way back here, just this term QDW. I haven't yet introduced the Durand differential, but I will assume. But I want to sort of just concentrate on this for a second. So this is the deformed symplectic cohomology, and you can obviously, variances this, you can look at the negative powers, the periodicized version, the homotopy fixed point, so the different versions you can take. But the most interesting is to sort of look at non-inverted Q. That's what I want to actually do. And so the theorem, which is the statement that was not in our paper, sort of, well, consequences of it are sort of assumptions into the theorem. But the statement is that you can write down, you can bulk deform this PSS log map to an isomorphism between H star, the cohomology of M with this formal variable Q, and then there's an additional piece which is the sort of thimbles and tangency, and that actually gives you, so you get an isomorphism to this deformed symplectic cohomology. And then, so the map will be sort of by definition the Q linear on this first part, and then if you invert Q, then it becomes an isomorphism of the at least the vector space of quantum cohomology with the Q inverted symplectic cohomology. You get more information. You remember sort of at least the full Gauss-Manin system by not inverting Q, so it's very interesting to not invert Q. Now, so the Q linear structure, meaning what you get by taking the Q linear structure, there's a clear Q linear structure on the target, and moving it over to the other side is it's interesting. So I don't actually understand it super well. There's kind of a hidden, these are kind of a hidden Q linear structure on that other sum end, and so basically it should be determined in some way by laws going with the variance, but we don't actually. Well, honestly, I haven't tried very much.
Somehow Q solution, and the other piece is somehow Q solution.
Yeah. So it is because right. Well, you'll see because Q. So let's say it like this. So if you just think about degrees, this is degree 2, and those degrees are sort of just homological degrees. If you multiply by something like Q, and so there's a lot of Q shortages in this Gauss-Manin system. So the part that's most relevant for us is what happens to because remember this theta is forming shared and this superpotential class. It lies in sort of the W = 1 part. So if you apply to that, then you basically just that's just like pushing forward the class into that. So in particular, theta Q times theta is C1, which again won't surprise the mirror symmetry people. Like the Markov element is C1. That won't surprise anyone. But then, so I wrote down some possible formula for what happens on W = 2. So one piece would just be multiplied by the first Chern class and lowering the filtration by So going W by 1, and then there would be a Gromov-Witten piece, which would be so a 2-pointed Gromov-Witten invariant of degree 1, with one constraint being the push forward of the class, and then beyond that, I haven't really. I'm not sure, but I think it should involve some relative Gromov-Witten invariance. Maybe be an interesting enumerative question. But okay, so in terms of like history of motivation, so like the above, so this theorem is it's a refinement of work. Well, to be honest, I'm not sure showing that we do is compatible with they do is in fact the work we haven't done, but in any case, Borman, Sheridan, and Bell, which they wrote down a spectral sequence from symplectic homology, adjoins Q plus minus to homology, and using these ideas, Mohammed Al-Alami and Nick Sheridan are also sort of working out some isomorphisms between Q inverted deformed symplectic homology and homology, but for us it's sort of nice to have the explicit map and one compares a connection on one side. That's relevant. But the motivation for us is sort of that the key motivation why we're interested in this is that the Raphkatai category of the complement is sort of extremely well understood homologically. And we're going to apply a lot of homological algebra techniques to the complement, and so basically that's we can use that homological algebra and take it to say things about homology. But it's again, this is sort of a decategorified version of things that are well known, Zeidel, the category, the compactification, the deformation of the complement, and so forth. So Nick Sheridan can say that many people. But it shows that you could really say things about quantum homology and so that's useful. So okay, so let me try to explain what this bulk deformed map is. So we're going to begin with you sort of when you have this direct limit, you can implement it at the chain level using a telescope. So these CF, these Floer groups are basically things that slope W plus epsilon. And what you were going to do, what we're doing is really, deforming. If you think about gluing in these, you take these thimbles and glue them in. You're looking at curves that are passing through the divisor at endpoints, but you're not actually. What's actually happening for Floer theoretic reasons is that you have to sort of view this as a map from something that's a slope W to, you have to keep sort of the slope and the number of mark points have to be sort of compatible if you want to write down a chain complex. And so, so the deformed telescope, it has a bunch of stuff in it. Well, let's say, I'm supposed to be able to point and stuff, but the standard pieces are just the things that have no Q in it. So this thing is the sort of diagonal piece here without any mark points is just a continuation from the slope 0 to slope 1. That's just the standard part, but we're going to add in a bunch of other stuff multiplied by Q. So the first row of the telescope has sort of connecting 0 to 1, you'll have one mark point intersection, connecting 1 to 2, one mark point, but there's also a term that has 2 mark points, Q squared, and so forth.
The mark points are breaking out in the logic.
Yeah, they can intersect. I sort of glued in all these signals, if I can do. And then, but there's also these sort of off-back, when you do this telescope, there's the analog of the continuations that pass through the divisor. So it's, that would be like this big diagonal term that's multiplied by 2. Or multiplied by Q, sorry. And So that's what we've got. And then, so the map. Oh yeah, and I should say that, like, you know, really when we're doing this theory, like we're thinking of this, again, you're still thinking of this, you know, basically your parameter space for defining these maps is like the space of you know, you could say M unordered mark points on the cylinder up to translation. So so it's like a parameterized count, and same here. So we're gonna just look at the you know, one count will have no intersection at this distinguished mark point at infinity, but we'll carry m mark points, and so it'll go into slope m Hamiltonian. And so that sort of gives you the part that's going to be, you sort of take this count and extend it linearly. And then the next part will be the sort of including this tangency. The distinguished mark point now will have a tangency of order W, and it'll go to slope again, slope m W plus m, and will sum over the overall m. So it's basically like a natural kind of bulk deformation. So if you set W or M rather equals to 0, you get this sort of thing I was saying before, these PSS log counts. And yeah. And okay, and so what we want to do is sort of think like, how can we get cohomology out of this? So so let's take the real oriented blow up, and you know, start with this kind of cochain, this thing called the log homology. You start with a cochain model for that, which is just has like homology of blow up within the same homology of x, and then also has this you know, Coulomb differential forms on the boundary, which is the circle bundle. And we're going to add in an additional term, which is this part that's multiplied by, I wish I could form. Anyways, this part that's multiplied by q, which basically would be, so on the n case, you first restrict the class to the boundary, and then you apply I lower star by upper star. And that will go from so the degree so from z equals to 0 part to the z equals to 1 part. And then on the zi part, the term is literally just I lower star by upper star. And in fluid theory, like just like maybe I should even say, but you're using sort of, you can do it with more state, it's a little bit easier. But Coulomb cohomology is maybe nicer to think about. And basically, if you take this, so this is the Coulomb cochain complex, it's an easy topological exercise that that there's an explicit map, which is from the source of my deformed PSS log map to this deformed log homology, which is basically the pi lower star is this. So pi tilde, sorry, is the blow up map, and so I pull back by pi tilde on the first factor, and I just also pull back along the boundaries. And that actually just defines the quasi isomorphism. So it's basically saying that these you know, these two sort of chain complexes I wrote down are acyclic. Probably is obvious to many of you. So what we do is, you know, we're going to basically copy the strategy from, you know, before we include these additional mark points. So you just, so we're going to include basically include these angles. So we're going to make a map from this log cohomology to basically this GUR is just like the basically the action zero. You know, again, we use like we arrays the actions are basically very close to the winding, the power of Q minus the winding number or something. And what we're going to do is basically just write a chain map using these symbols with angle constraints from the like, you know, this if you stare at this this complex here, the Q deformed log cohomology, it actually has a natural grading by so the differential, if you look at the power of Q minus power of Q minus the power of Z, that gives a grading. And so you know, you look at the grading zero piece that will basically, so it's the same thing, but include the same map, but including these angle constraints. So every time you say circle bundle, you're imagining that you're putting in an angle constraint. And basically, so it turns out you get a chain map in this way. So maybe it's useful to say, so I guess in Morse theory language, maybe useful to say like where this additional term in the differential comes from. So like this part it's multiplied by Q. So like if I'm not, like I'll just look at the boundary. So I have the circle bundle. I can basically arrange for the Morse complex of my circle bundle SD to be sort of two copies of the Morse complex of circle bundle, two copies of the Morse complex of B, where you know there's sort of a cross term. You have the Morse differentials on these pieces, and then you have a cross term that represents multiplication by the first term class. And you know, basically, if the stable manifold of these pieces here are basically like sections over D, and these other pieces here, they're sort of almost fill out the whole circle bundle. And so so if you think about in Morse theory, this map pi upper star, pi lower star, it's a very simple map. What it does is it just, so I have a section, I'm over here, I have a section, I map it down to D, and you know, and then I pull it back, that basically takes this factor here to this other factor. And so what's happening? So now I'm imagining that I have some constraints, you know, along a section. And I have a bunch of, I have my distinguished constraint here along the section. And where this additional term in the differential comes from is so this term, it raises the power of Z. Where it comes from is this like one of the mark points goes to infinity. So in that case, you sort of lose the, you know, there's no way to make an angle constraint anymore because you lose the direction of fluid, but the tangency goes up by 1. So so that's basically an explanation for why I'm not going to write it down. For why you get a chain map. That's basically this minus W braided pieces, and then, you think a little bit about the other piece, it works out. And, we already know what I told you already is that when you set Q equals 0, these maps basically recover this low energy, isomorphism of the first beta spectral sequence. So that tells you that these maps, are quasi-isomorphisms. And then, an additional thing that happens is, obviously, if we think about just pulling back, if we pull back to, so here, like I was saying, the pulling back is basically the pullback map in this sort of Morse model for the circle bundle is very easy. This takes, it's basically this copy of the Morse cochains. And then, as I said, like the stable manifold here is basically like almost, the preimage. So putting an angle constraint here is not really actually putting an angle constraint at all. So what that tells you is, if you pull back, if you use this pullback map and apply the map that I have, that's going to be the same as this full log PSS map. And so these filtered pieces are quasi-isomorphism, and so the whole thing is a quasi-isomorphism. So okay. So and then but that's not the full kind of Gauss-Bonnet system. So you also want to sort of include this Durand differential piece, and so the way that we do that is sort of well understood in Floer theory. So so we kind of work over the classifying space of S1. There's sort of a convenient model that we use for this, which is just to think about basically our cylinders are coming with additional like angle decorations. So basically there'll be a bunch of additional circles on the cylinder that are, but when the cylinders collide, and we think of sort of the Floer, the Hamiltonians have to be suitably rotated. So you start with the Hamiltonian, the Hamiltonian here will be rotated by the sum of the different angles at the output, and if you do sort of Floer cohomology over this space, then you can also insert a bunch of mark points here on the cylinder, and what you've got in total is that the S1 the statement is that the S1 equivariant symplectic cohomology becomes an L infinity module over this symplectic cohomology. And so I can also, what I can also do is twist that one and find my Markov class, and that will give me, again, there's different variables. Now you can invert U, invert Q, and so forth. So there's like 6 different variants you can do, but again, the one I want to do is inverting neither, and in that case, so the claim is that there is this. I mean, this here, so sort of, it's like a 2-color dot. So yeah, I don't know if it, I mean, maybe somebody can answer it. That's a general statement. Here we can do it sort of.
I'm trying to understand whether it's part of the structure of the symplectic cohomology. Anyway, I feel like that kind of different things that are theory.
okay, yeah. But in this case, it's, you can write it down. And the statement we have in this, I mean, put it. Yeah, you know, maybe I'll try to say something like, is that so, you know, you can make these maps that I said, that I wrote down before, equivariant, and you have and what it looks like here is a cohomology, the cohomology that joins Q and U, and you have this, again, this piece with the divisor, and then again as well after inverting Q, so the order maybe matters a bit. No, never mind. So but you invert Q, then you have an isomorphism with the really what's really the state space of the quantum connection. So and it kind of raises an interesting question, maybe that I'll finish like this talk with, which is if you go back here, so you know I was not super careful about putting in. I'm going back to the mirror symmetry picture. It's something that I don't know that I think is sort of would be interesting to sort out. If you go back to the mirror symmetry, I wasn't careful about putting in the U variable. And I was really thinking, in classically, the variable Q here is like really Q over U or something. So it has degree 0, whereas non-commutatively it has degree 2. But here, so it's known that if you set up a version with mu and Q, then if you invert Q, it's flat over U.
Which one is U and which one?
U is the equivariant parameter.
So when L
Eligible. I think, okay, here,
the other side of that.
okay, you don't understand what this is like. So the U, okay. So U, okay, so on the algebraic geometric side, you want to know what the actual complex is. So it would be.
Yeah, well, we said there should be Q and U.
Yeah, okay. So it would be so we would adjoin U as well, and we would consider U, the differential would be U d theta, or plus yeah, Q dw, where's theta? We have a complex like this, and is U is degree 2. Because the Durand differential, remember, there's the gradings don't in non-commutative don't actually map. So, but it's known that if you invert Q, then it's flat over U and finite dimensional. That's like Monsevich and various people. But what we seem to be getting is in symplectic topology, you get sort of flatness over U without inverting anything. So I don't know if that's just not true, and you know if that's something special to symplectic geometry, or if there's like a modification of the argument, which may be a question for algebraic geometry. So I'll stop there.
Let's say that